Okay, so we are going to do the series circuits next few pages. I believe it's 11 through 13. Don't forget, if you want the online reading material, it's the physics classroom stuff. I put it on Canvas in the circuits, module, and it says series circuits optional reading material. So remember that parallel circuits have separate pathways for electrons to flow, and series has like one pathway for electrons to flow. So let's look at number one. Electrical devices and circuits can be connected to each other in a number of different ways. The two most common connections are series connections and parallel connections. Observe the electrical wiring below, indicate whether the connections are series or parallel. Alright, so we got the left one and the right one. We know that series, there's only one pathway. Parallel, there's multiple pathways. So this one's not real hard. It's not real hard. It's not real tricky. The one on the left is parallel, and because it has multiple pathways. The one on the right is series because there's just a single pathway, right? Okay, let's look at number two. Two electric circuits are diagrammed below. For each circuit, indicate which two devices are connected in series and which two devices are connected in parallel. Okay, so this is talking about, these are two separate things. So they're saying, of these four devices, speaker, bulb, resistor, ammeter, which two are in series and which two are in parallel? Again, this one's not real hard. It's just kind of figuring out what they're asking. So if we look at this in series, in other words, one pathway, the ammeter is in series, and the resistor, because there's just one pathway, it can flow along those two, and then the multiple pathways would be the bulb and the speaker for the left one, which makes sense, right? So that's the left side. The right side should be just as easy. So the things that have only one pathway, speaker in series, ammeter. And the things that have multiple pathways, which is a parallel, would be the bulb again and the resistor. It's kind of noteworthy that usually bulbs are connected in a parallel because bulbs tend to burn out, right? And if they burned out, the whole thing is done. So that's why bulbs usually are in parallel. So this can be changed out and everything keeps functioning if it is out, right? So let's do number three, comparing series versus parallel circuits. Fill in the table below to indicate the manner in which series and parallel circuits differ. Okay, so series circuit. Let's move this up just a little bit. There we go. There we go. All right, the pathway by which the charge loops around the circuit is characterized by blank pathways. They're looking for a number here, and at that point it should be, pretty easy, honestly. So in a series, it is just one pathway. And in parallel, you're not going to put two because really you could put infinite number of numbers, right? So we're just going to put multiple pathways. Awesome. Okay, so if one light bulb goes out, the other light bulbs, what? We kind of just talked about this. We talked about this when we were talking about this one. So in a series, when it's one single pathway, like this one, if the light bulb goes out, the other light bulbs will also go out. Right? Because the connection is broken here. There's no other pathway it can go. Whereas in a parallel, if one light bulb goes out, the other light bulbs will stay lit. Think about this. If you're hanging up, lights on your house or something, you would definitely want to hang them up. You definitely want to use like a parallel circuit, because imagine if one light bulb goes out and you have 100 bulbs. If you're using a series, you have no idea which one went out. You've got to literally go check and replace each bulb until you find the one that went out, right? Or switch them around. That would be a huge pain. So that's why parallels are very beneficial. Okay, let's look at the next one. As the number of resistors is increased, the overall current does what? So in a series, as the number of resistors is increased, the overall current will decrease in a series as you increase resistors. So this is decrease. And then you know this one's probably going to be the opposite. So again, as the number of resistors is increased, the overall current in a parallel circuit will increase. These last two are very important, and you're going to run into these over the next several pages. All right, D, last one. As the number of resistors is increased, the overall resistance is increased. In a parallel circuit, as the number of resistors is increased, the overall resistance decreases. So again, let's say that again. These last two are very important. As you add resistors to a series, so this is our series, as you add resistors, more and more of these, the overall resistance will go up. Makes sense. In parallel, it's different. As you add resistors, the overall resistance will go down. Okay? So, again, very important. And when we get to stuff where we're going to use our formula, the formulas are very different for calculating resistance. Okay? So, let's go to the next page. Okay. So, number 4. Ooh, let's refocus that. That is not focused. Okay, so let's do number 4. I'm kind of pausing to gather some notes and stuff, and go back over with you guys. So, number 4, the following diagram represents circuits consisting of 2 electrical devices connected in series. What we're going to do is fill in the blanks to show the voltage drop. So in a series, this is important to know. This is change, our triangle, right? The change in voltage of the battery, which is like this or this, equals the change in voltage of each point where voltage drops or is used, like power is used more or less, right? So when we look at this one, our battery says 120. The 120 is our battery, and this is our series. Equals the voltage drop of our blank plus the voltage drop of this one, which is 80. You could say the voltage drop is essentially negative 80, but we're just going to say 80 here. Which means this voltage drop has to equal, this plus this has to equal 120. I mean, you guys probably already know it by now. 80 plus 40 is 120. So this is negative 80, so we're going to go negative 40. Following our rule in a series, the battery's voltage is, as it drops, it should add up to the initial voltage, right? So this one is going to be pretty easy too. So our battery's voltage is 12 equals the drop here plus this unknown plus 4. So really we're sitting on 7 and it has to equal 12, so the only thing to do really is put a 5 here, right? So the total voltage drop is 12. It's 3 plus 5 is 8, 9, 10, 11, 12. Okay? So that is the first deal. Now let's do number 5 before we, let's just finish this page. So the voltage flows from the positive to the negative, where there's a electric potential difference. So first we need to put our arrows in for it flowing. So come up here, it flows around, and then it flows back up. So then the question is, from the starting point, what has the most voltage? Okay, so first one is the voltage of A, which is right here, or the voltage of G, which is right here. Well, remember, G is the ending, right? So it's always going to start, it's coming out of the battery. It's going to start with the most voltage. Just like if you go to the mall, the second you step into the mall, you have the most money. And every store you go to, you lose a little bit of money as you spend it, right? So A is going to have our highest voltage. Then let's look at this one, B versus C. Well, again, you spend a little money here, but you should have more money at B than you have at C. So B will have the most voltage. B versus F. Again, B will have the most voltage. And we are going to go over this current. And I'm actually going to bring you guys to the reading page on Physics Classroom, which is on Canvas, and we'll look at that. Okay, are we ready? So we're going to go over a lot of things right now. It might be confusing at first, but okay, take it slow. You're good to go, right? So let's talk about the rule for current. So right now it's saying, the current of A is what to the current of G? So there's A. Let me just go in here. There's A, there's G, right? So let's go back to our reading material online. And we see that the current of the battery is equal to the current of 1, which is equal to the current of 2, which is equal to the current of 3, and so on and so forth. So in other words, if you read right here, current, which is the rate of flow of charge, is everywhere the same. So it sounds weird, everywhere the same, but that means like current is the same throughout the entire series, right? So it is the same at the first resistor as it was at the last resistor, as it is in the battery. So our formula here, the current of the battery equals, it's all the same, this current for each one of these, which equals the change in voltage divided by the resistance. So a lot of info, and we're going to go for some more in a second. So first let's go back here and let's see that the current in A we know is equal to the current in G. And we can just, before we even do any of these, we know, again, A and F, the current will be equal. The current is equal throughout the whole thing, right? So let us go back here and check some stuff out. So again, this is on Canvas. So if we scroll way, way down, let's talk about this. It's very important, even though it's probably going to be confusing. And sometimes I even get confused explaining it, but it is what it is. So we know that we talked about resistance, and we said that the resistance of each in a series always equals the total resistance. So there's no trade, straightforward. So the total resistance is I'm trying to point at the screen with my pen. It ain't picking that up. 17 plus 12 plus 11. So the total resistance is 14, right? So let's see if we can bring this off to the side. There we go. So our total resistance is 14. Sorry, 40, not 14. Right? Our total voltage is what? Well, if we look over here, 60, right? So our voltage equals 60, which means our amps is 60 divided by 40, right? Because our amps equals voltage over resistance. So our amps, which is I, equals, what do we say, 1.5? So we know, if we scroll down here a little bit, we can say that the amps obviously are the same, but we can also figure out the voltage drop. So remember on that page we just did, we could calculate it because they kind of gave us the voltage, they gave us some of the voltage drop, but if they don't give it to us, we can figure it out, right? So let's look at this. I know it's going to be, let me see if I can stretch it out. It's probably going to cover the screen, but you can look at it on yours too. So the voltage of 1 equals the amps times the resistance of 1. So the resistance of 1 equals 17. So let's write this down. So the voltage of 1 equals 1.5 because the amps are always the same, times, I'm just going to put it in parentheses because the dots can be confusing, the resistance of 1. Therefore, and all we did is rearrange this formula. Oh, there you go. This formula here, we just rearrange it, so no worries. So therefore, the voltage of 1 has to be, as they said, 25.5. Right? I'm not going to write the rest, but I am going to kind of go through it. So we figure out the first voltage, knowing that the total voltage drop will be 60, so that each of these the voltage drop added together will equal 60. So we know we have 60 minus 25.5 left. And you see the answers anyways, but let's go through it. So the voltage of number 2 is the current of number 2. Remember that the current never changes, so it's still 1.5 times the resistance of number 2. What's number 2 resistance? Without looking at the answer, we just look up here. It's 12, right? 1.5 times 12, 18. Okay, so you could figure it out what's left over because we know the total voltage is going to be 60, but let's just go with it. So again, the voltage of the third will equal the amps, which is 1.5, doesn't change, times the resistance, which is 11 at number 3 resistor, which means the third voltage will be 16.5. If we add that all together, 25.5, let's see, plus 16.5 is 26 plus 16, 36, 42 plus 18 is 60. So you see how that all adds up? Everybody's probably super confused, but I promise you'll use this a few pages later. It'll be super confusing, but look at this sheet. It'll help you. Ask me, I'll help you out, right? So let's finish, and this is on Canvas, so you guys have this too. Let's go ahead and finish this side. So here we go. Voltage. The voltage in A versus the voltage in F. Remember, first thing, it's leaving from the plus, the positive, so let's draw that out because it says to draw it. Okay? It's never going to be higher than when it leaves the battery, more or less, right? So F is definitely going to be higher, which means we got to make it like this. All right, the voltage of B versus the voltage of C. B, C. So again, C is going to have much more current, or excuse me, voltage. Sorry, oops. We know the amperage is the same. Okay, minor confusing thing here. Don't be confused. So the voltage in D compared to the voltage in F. So let's make sure, because I know we're in a roll, so you want to just start slashing stuff, but don't do that. So let's look at D and F. So think before you write something. Is there anything between D and F that would cause the voltage to drop? Is there a light bulb in between D and F? Is there a speaker? Is there a resistor? Since the answer is no, the voltage is not going to drop between those two. Make sense? So that's why this is going to be equal. Because there's nothing. It'd be like when we're talking about our mall analogy. When you go to the mall, if you walk in and from point A to point B there's no stores, does the money in your wallet reduce or decrease? No, because there was no stores. There was none of these stores to take your money and lower your money, right? So again, your voltage will be the same. So that's why this is equal, right? So I know you get in the habit, you're like, oh, boom, easy, easy, easy. And then you get a curveball. So you got to slow down and check these out. All right, let's look at number 5. Express your understanding of equivalent resistance by filling in the blank. Equivalent resistance is super, super easy. I'm going to pull this thing up again so you guys can check it out. Let's go. Okay, well, here it is. So equivalent resistance equals, you just add up all the resistances, right? So the equivalent resistance was 40 because you added up 17 plus 12, blah, 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 blah. Easy. So having 2 4 ohm resistors, the equivalent resistance should be, well, it's just 2 times 4, right? So if we have our series like this, and there's one here that says 4, and there's one here that says 4, little horseshoe thing, it's 8, right? So this part's pretty easy. So we're talking about a series. Remember, we're talking about a series. You just add them up. Series is easy. So having 3 4 ohm resistors, I mean, it shouldn't be, it's not rocket science. 3 times 4 is 12, right? And again, having 4 4 ohm resistors, 4 of these, 4, 8, 12, 16. Easy money. Okay, number 6, and we're done with this page. Dang, we're losing focus. It's hard. Hang in there. Electricity's hard. Get that focus. There we go. 3 light bulbs are connected in a series. Okay? The filament of one of the light bulbs burns out. So keep this in mind. This is our light bulb, right? Electricity comes in. There's this little filament goes out, continues along the pathway. So when they say this filament here, which is the connecting wire, burns out, it's broken. So the remaining 2 light bulbs will still be lit. Well, no, because electricity goes here, here, and then it can't go because it's broken. Yet their brightness will be noticeably less. Well, actually, no, because they won't be bright at all because they have no power since it's a series, right? So this one is false. Good job. We're 20 minutes in. You're doing great. Okay, so let's move on to the next page. We got one more page. I will say this page, much easier than the last two, which the last two weren't even hard, to be honest, but this page is pretty easy. So, remembering our rules. The total resistance is in a series, which is this, equals the sum of all the resistances, right? Analyze the following circuit and determine the equivalent or total resistance. Okay, same thing. Then determine the current. Okay, so step 1, let's do the total resistance. 2 plus 2 plus 2. 6, right? Easy. Let's do our little horseshoe sign. Okay, current. The current, let's do our formula for current. Equals, can we see this? I equals voltage divided by resistance. Right? So, in this case, and remember the stuff we just talked about, so it's kind of like the voltage at that level divided by the resistance at that level. So in this case, it is going to be 2 amps. And remember, the current's the same at all these, right? So, let's do this one. The total resistance equals 6 here, plus 4, plus 2. 7, 8, 9, 10, 11, 12. Remembering this deal we did from our worksheet, equivalent resistance equals add them all together, right? That's exactly what we just did. All right, current. Current equals our voltage divided by our resistance. Therefore, our voltage is 6, our resistance is 12. Don't say 2, because it's 6 divided by 12. Don't say 2. Everybody's like, oh, it's 2. It ain't 2. You flipped them, right? 6 divided by 12 equals 0.5. You can put 0.5 if you want. I don't like to waste my ink, so there it is, right? Okay, cool. So we did that. Let us move on to the next one. All right, pause for station identification. Are you ready to rock? Don't move too fast on these. Let's get some light going. Can we get some light? There we go. It's lit up. All right. Current equals. This is the simplified version of this formula, right? So we're doing a series. Our voltage is 120. Our total resistance, our equivalent resistance, is 60. Therefore, our current throughout the whole system is, just cancel that 0 out, 2. Okay. Let's look at this one. Give it a shot. Pause it and give it a shot. I bet you get it wrong, but I hope you don't. Hopefully you don't go too, if you don't go too fast, you'll get it right. If you go too fast, you get it wrong. All right, let's do it. So, again, current equals voltage over resistance. Our current, hey, there it is, 2. 2 equals our voltage, 24. Our resistance, therefore, what goes into 24 to get 2? Hopefully you said 12. So, is that 12? No, it's not 12, because this is the total, or the equivalent resistance, right? So really it's 12, 11, 10, 9, 8, 7, 6. So this is 6, because remember, the total resistance is 6 plus 2 plus 4. Right? Good. Hopefully you guys did not put 12. If you put 6, you're ahead of the curve. All right, man, that is so bright. It's too much. I'm trying to find that balance. Can't find the balance. We're going to find it. All right, so, oh, another one. Current. Repetition is key in physics, guys. I've wrote this same formula 1, 2, 3, 4, 5 times with just letters, not counting when I plugged in numbers, right? So repetition is key. It's only a few letters and it ain't going to kill you. So, voltage, 24. We don't have our resistance total. Current, 2.4. 2.4 equals 24. What goes here? So, we'll call this R. Well, we don't have to. Yeah, we do. All right, so let's do some algebra. We can do this a number of ways. I'm just picking a way to do this. So I'm going to multiply this side by R, cancel. So now we have 2.4R equals 24 divided by 2.4 divided by 2.4. And you should have gotten, what is that, 10? 24 divided by 2.4, 10, yes. So our total resistance equivalent, is that still on there? Yeah, equals 10. Is this 10? No, right? Because this is our total. 10, 9, 8, 7, 6, 5, 4, 3, 2. Oh, so this is 2. Because remembering the formula, the current, let's bring it back. Let's bring it back to that page. Equals, equivalent resistance, sorry, equals the current. Oh, why do I keep saying current? The equivalent resistance equals the resistance of each, resistor. We'll say, right? Stop resisting. You guys are going to get this. Yeah. All right, let's look at this. Oh, this time they don't give us voltage. So we're going to, again, current equals voltage over resistance. Our current is what? 3. Our voltage is, we don't know. And our resistance is 2, 4, 5, 6. Well, that's easy. So we got to get the 6 out of there. Since it's dividing, we're going to multiply this side by 6 over 1. It's the same thing we've been doing, because 6 over 1 is just 6, right? Cancel, times 6, voltage equals 18. So is it 18 here? Is there any tricks? No tricks. 18. Easy, right? Now there's we could figure out how we talked about earlier, we could figure out how the voltage drops each time. It's going this way. Let's add this. I forgot to put this in. This is going this way. This one's going this way. And this one is going this way. Cool. So voltage is 18, 18. Is that it? I think we're done. Yeah, the next one's parallel. Congratulations. You did it. You all did it. We finished series. Good job, everybody. And we did it in under 30 minutes.